So we are continuing with eigenvectors, eigenvalues. Today we're going to talk about diagonalizing a matrix, and that's going to allow us to solve systems of linear equations, which is what we will do tomorrow and Thursday. And solving systems of linear equations is a huge thing which you're going to be seeing again and again and again in your courses. So today's lecture has to do with, okay, so when I first introduced eigenvalues and eigenvectors, I gave you some matrix, and I was able to write it as in this form. And I had some matrix that was like a 3 by 3 matrix, and I was able to write it as the inverse of a matrix times a diagonal matrix times a matrix. And the question was, where did that come from? How did I find this diagonal matrix? Because we found that knowing that a matrix could be written in this form allowed us to do some pretty cool things, like compute the 40th power of the matrix easily. But I kept deferring the question of how did I even write this decomposition? So that's what today's lecture is going to be about. It's going to be, when can you write a matrix as a product of some matrices and a diagonal matrix? And that's called diagonalization. But before we get into diagonalization, let me just remind you from the last time of the definition of an eigenvalue and an eigenvector. So A is square. Lambda is an eigenvalue of A if there is a nonzero vector V such that A times V is equal to lambda times V. We call V an eigenvector of A, and we say that lambda V is an eigenvector, eigenvalue, eigenvector pair of A. So that's just language. From the last lecture, we saw that if someone gives you a matrix, then to find the eigenvalues and eigenvectors, it was just a procedure that you had to crank. So given a matrix A, to find its eigenvalues and eigenvectors, okay, so the first step, step 1, find all solutions of the determinant of A minus lambda I equals 0. So first we computed what the determinant of A minus lambda I was. This was some hideous polynomial. If A was a 2 by 2 matrix, it was a second degree polynomial. If A is a 3 by 3 matrix, it's a cubic polynomial. If A is a 4 by 4 matrix, it's a quartic polynomial. But one way or another, this thing is a polynomial. You seek its roots. If you have a 10th degree polynomial, it will have 10 roots. If you're lucky, you'll be able to find them. The roots are the eigenvalues. Step 2, for each distinct eigenvalue, find the general solution of A minus lambda I times x is 0. And this is how we found the eigenvectors. So for example, if A has eigenvalues 1, 2, 3, so if the eigenvalues are lambda equals 1, lambda equals 2, lambda equals 3, we need to solve 3 homogeneous problems. The first one would be to find all solutions of A minus 1 times the identity times x equals 0. That will give you eigenvectors for eigenvalue 1. Then you have to solve A minus 2 times the identity times x equals 0. That will find you the eigenvectors corresponding to eigenvalue 2. So let's say A is 3 by 3. And if A, for the third one, we have to solve this problem. So here we write down the augmented matrix. We carry it to reduced row echelon form. That gives us one eigenvector. Here we write down the augmented matrix. We carry it to reduced row echelon form. That gives us an eigenvector for this. Here we write down the augmented matrix. We carry it to reduced row echelon form. That will give us an eigenvalue for this, an eigenvector for eigenvalue 3. So we would get eigenvector, eigenvector, eigenvector. We would get 3 eigenvectors. And it will turn out that those eigenvectors are actually linearly independent. The more challenging case might be something where A is 3 by 3 and has eigenvalues 1, 2, and 2. So the characteristic polynomial is going to be a third order polynomial. It's going to have 3 roots. It might turn out that those 3 roots are 1, 2, and 2. So we would have a double root. This would mean that the determinant of A minus lambda I is minus lambda minus 1, lambda minus 2 squared. That could happen. So the good news is that when you're looking for eigenvectors, you have less work. So we need to solve A minus 1 times the identity times x equals 0 to find eigenvectors for eigenvalue 1. And we need to solve A minus 2 times the identity times x equals 0 to find eigenvectors for eigenvalue 2. So on the one hand, we're happy because for this case, we had to do how many reduced row echelon form calculations? 3. That's more work. On the other hand, each one is guaranteed to give us an eigenvector. Here, we only have to do two elementary row operation calculations to find the general solutions. So that's less work. But in this case, the general solution might have 1 or 2 free parameters. If there's only one free parameter in the general solution, that means there's only one eigendirection. We'll get one eigenvector for this eigenvalue. We get one eigenvector for these eigenvalues. If there are 2 free parameters, then we get 2 linearly independent eigenvectors, both with eigenvalue 2. And from the last lecture, we saw that any linear combination of eigenvectors will still be an eigenvector as long as they have the same eigenvalue. So this is going to be something that we need to very much keep in mind for today's lecture. So this is a review from Thursday. Are there questions? Okay. So let's start with an observation. So let's take the matrix A, which is 3, 1, 1, 1, 3, 1, 1, 1, 3. And here's a matrix P. And in the first column is 1, 1, 1. In the second column is minus 1, 1, 0. And in the third column is minus 1, 0, 1. Now I'm going to compute A times P. So A times P. So in the first row, I have 3 plus 1 plus 1 is 5. Now normally I go across by rows. I'm going to, usually when I multiply A by P, A times two matrices, I go boom, 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 boom. I'm going to do it by columns this time so that you can see something. All right? So anyway, 3 plus 1 plus 1, there. 1 plus 3 plus 1. 1 plus 1 plus 3. So I want you to believe that I just did A times the first column of P. So I'm writing this as first column, second column, third column. So do you see that when I multiply A times P, that the first column of A times P is the exact same thing as A times that vector? Do you see that? This is super important. Please don't lie. Do you understand that the first column of A times P is the same thing as A times this? Okay. Now, let's do the second column. So we have minus 3 plus 1 plus 0. It's minus 2. Minus 1 plus 3 plus 0 is 2. Minus 1 plus 1 plus 0 is 0. That was just matrix multiplication. On the other hand, if I had just viewed P as column, 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 this middle column of A times P is precisely A times V2. Third column, minus 3 plus 0 plus 1 is minus 2. Minus 1 plus 0 plus 1 is 0. Minus 1 plus 0 plus 3 is 2. That is the same as A times V2. V3, thank you. Now, looking at P, I see that I have this column is the same as what? How does this relate to the first column of P? 5 times V1. This relates how to the second column of P? 2 times V1, V2. And this? 2 times V3. All right. Okay. This is just a general fact of matrix multiplication. This has something very special to do with A and how P was chosen. This. That's because these columns are eigenvectors, and those are the eigenvalues for the eigenvectors. Now this, I claim, is the same thing as V1, V2, V3 times the matrix 5, 0, 0, 0, 2, 0, 0, 0, 3. 2. So I'm claiming that this thing is that. So let's check. Again, I'm just going to do, so here I would have 5, 0, 0. That would give me 5 times the first entry of V1. If I went down one row, I would have second entry of V1 times 5 plus 0 plus 0, and so forth. So what have I figured out? I have figured out that A times P is equal to P times 5, 0, 0, 0, 2, 0, 0, 0, 2. That's one thing I figured out. The other thing I figured out is, in general, if V1, V2, Vn are eigenvectors of A, and P is created from them, then A times P is equal to P times the diagonal matrix with the corresponding eigenvalues. So I checked it by hand for this specific example. Let's just see why it's true in general. So A times P is A times V1, V2, Vn. That's by the definition of P. This is equal to, the first column is A times V1, second column is A times V2, up to A times Vn. This is by matrix multiplication. This is equal to, I assumed V1 is an eigenvector, so A times V1 is lambda 1 V1. I assumed V2 is an eigenvector, so lambda 2 V2. And lambda n Vn. This is because Vi is an eigenvector. And then this is V1, V2, Vn times the matrix lambda 1, lambda 2, lambda n, and zeros everywhere else. So that's by matrix multiplication. So this is just a general fact. Yes?
That first step that you have on that board, is that same definition of P or determining?
Definition, thank you. The definition of P. So I was taking P and I was building it out of eigenvectors of A. All right, so this tells us that if I go to this example, so if I have A is 3, 1, 1, 1, 3, 1, 1, 1, 3, and I take P, which is 1, 1, 0, minus 1, 1, 0, minus 1, 0, 1, then I have that A times P is equal to P times, I did that calculation, 5, 0, 0, 0, 2, 0, 0, 0, 2. If P is invertible, then P inverse A times P is equal to what? So multiply this by P inverse on the left-hand side. So take this equation, multiply both sides by P inverse on the left. Then I get this. I diagonalized A. But this depended on if P is invertible. Is this P invertible? What's a fast way of checking if this P is invertible? So here we get into the thing of, okay, it's invertible if its rows are linearly independent, if its columns are linearly independent, if its rank is equal to 3, if its determinant is non-zero. So we've got at least 4 ways of checking if this puppy is invertible, right? For this particular one, which is the fastest? Determinant, because we have those zeros. So let's check. The determinant of P is, so I'm going to expand about the third row. So I get 0 times that determinant, minus 0 times that determinant, plus 1 times that determinant. 1 times the determinant of 1 minus 1, 1, 1. And that is 2. And in fact, the inverse of this particular P, I computed, and it is 1/3, 1, 1, 1, minus 1, 2, minus 1, minus 1, minus 1, 2. And you can check in the privacy of your own home that P inverse times A times P really is diagonal. This matrix times this matrix times this matrix really is that matrix. Now, say I had taken A to be the exact same A, 3, 1, 1, 1, 3, 1, 1, 1, 3, and I had taken P to be, let's see, minus 1, 1, 0, 1, 1, 0, minus 1, 0, 1. This is a new P. This new P, let's call it P. This is a different matrix P. How is it related to the old one? I shuffled the columns. Is this matrix suddenly going to be non-invertible? No. Because if that matrix is invertible, its columns are linearly independent. Are these columns linearly independent? Does shuffling columns change linear independence? No. So P is still invertible. Or this P is invertible. Now, when I compute P inverse A times P, what's going to happen? Well, the machine that's running in the background is the following. So I know that when I hit the first column of P with A, I'm going to get P times some number. Yes?
Is the P on the top right-hand side board supposed to be equivalent to 1 middle top board?
Sorry, what?
Is the P matrix on the top right board supposed to be equivalent to the 1 in the middle board there?
Those are identical matrices. Hold on. Yes. That's bad. That's, okay, so I should have computed. It is supposed to be the same, and I need to compute my determinant more slowly, but it is still non-zero. Thank you. It's supposed to be the exact same matrix. It's supposed to be the exact same matrix. That was a copy error. So then showing that this is invertible, computing the determinant is still pretty much the fastest way because you have a bunch of ones. But yes, thank you. This is still the inverse. This is a copy error. So here I've shuffled those rows. I've shuffled those columns. So when I shuffle the columns, what's going to happen to the diagonal? So what's running in the background, this is always going to be true. This is always, always true. And then if P is invertible, I'll be able to write P inverse AP is diagonal. But this is the thing that's running in the background. On the left-hand side, I'm going to have this times that. What's going to be the eigenvalue for this eigenvector? 2. Then I'm going to have this times the second column. What's the eigenvalue? 5. Then I'm going to have this times that. What's the eigenvalue for that? 2. So if a matrix is diagonalizable, there's a whole bunch of different ways of doing it. First of all, you can shuffle the columns. You can shuffle your eigenvectors, and that's going to shuffle the diagonal. Secondly, if I had taken P, and instead of minus 1, 1, 0, 1, 1, 1, minus 1, 0, 1, I had replaced the middle column with pi, pi, pi. Is pi, pi, pi still an eigenvector with eigenvalue 5? Okay, we need to look at that. So let's look at 3, 1, 1, 1, 3, 1, 1, 1, 3 times t, 1, 1, 1. In my case, I chose t to be pi. All right? So if t were pi, I'd have pi, pi, pi. T is a number. Can it run through matrix multiplication? Yes. So this is going to be t, a times 1, 1, 1, which is t times, what is a times 1, 1, 1? 5, 5, 5. So this is going to be 5 times t times 1, 1, 1. So 1, 1, 1 is an eigenvector with eigenvalue 5. What about pi, pi, pi? Is it an eigenvector with eigenvalue 5? Minus 20, minus 20, minus 20? Eigenvector, eigenvalue 5. So not only can I shuffle around the eigenvectors, which shuffle around the diagonal entries, but I can take any eigenvector and multiply it by a non-zero number. And that will give me a matrix so that P inverse times A times P is a diagonal matrix. So whether or not a matrix is diagonalizable, the answer is if I give you a matrix, yes, it's diagonalizable, or no, it's not diagonalizable. Each student might come up with a completely different P, and with three eigenvalues, there are only so many permutations of the diagonal, but it's possible that you and your neighbor would end up with different diagonal matrices. So do people understand the degrees of freedom here? All right, yes?
For the diagonal matrix, why the first column's number is 2? How do you get it?
Okay, so this was the calculation that A times P, that if P is V1, V2, V3, where these are eigenvectors, then A times P is going to be lambda 1, V1, lambda 2, V2, lambda 3, V3. That uses the fact that these columns are eigenvectors. And this is the same thing as V1, V2, V3 times lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. That's by how matrix multiplication works. So the reason I had a 2 here is because this is an eigenvector of this matrix with eigenvalue 2. The reason I had a 5 here is because this is an eigenvector of this matrix with eigenvalue 5. But the key thing, the big, big, big thing that you need to get is that. And that this is true if the columns are eigenvectors. Negative 2. Is negative 2 an eigenvalue? I don't think negative 2 is an eigenvalue. So let's check. Let's just check that I have an eigenvector. I did this multiplication at the beginning of class, actually, when I had this matrix times this was this. So that is 5 times this. This matrix times that is 2. That's this, and that's 2 times that. And this matrix times that is this, which is 2 times that. So this multiplication I did slowly, carefully, and correctly. Then we looked up at P, and we realized that we had this is 5 times the first vector, this is 2 times the second column, this is 3 times the third column. The only difference between this example and this one is I changed the order of the first and second column. So if I multiplied this out, I would get 2, 5, 2. All right, so one last example. So what if I had said this matrix, and I had said P is 1, 1, 1, minus 1, 1, 0, and 10, minus 10, 0. I can check that A times P is equal to P times 5, 0, 0, 0, 2, 0, 0, 0, 2. Because A times the first column gives me 5, 5, 5. A times the second column gives me minus 2, 2, 0. Is this third column an eigenvector? Yes, it's a scalar multiple of an eigenvector, a non-zero multiple of an eigenvector. Its eigenvalue is 2. So this is certainly true. Do I have, can I write P inverse AP equals 5, 0, 0, 0, 2, 0, 0, 0, 2 for this P? Yeah.
I think the P is linear dependent, right?
Exactly. Thank you. So the answer is not invertible. These columns are linearly dependent, right? This column is a scalar multiple of that column. These 3 columns are linearly dependent. And so I cannot write it for this particular P. So this is a bad way of trying to construct a matrix P. Another bad way of trying to construct a matrix P so I could have had minus 1, 1, 0, minus 1, 0, 1, and minus 2, 1, 1. So if I had made this choice, I can check that A times P is equal to P times 2, 0, 0, 0, 2, 0, 0, 0, 2. Here, this is an eigenvector. This is an eigenvector. Eigenvector with eigenvalue 2, eigenvector with eigenvalue 2. This one is a sum of these two. It's certainly an eigenvector of eigenvalue 2. So it's certainly true that AP is equal to P times 0, 0 times that diagonal matrix. Is this P invertible? No. So whenever you're trying to diagonalize a matrix, it comes down to first finding the eigenvalues, second finding the eigenvectors, and third seeing if you can find a full set of linearly independent eigenvectors. If you can, the matrix is diagonalizable. If you can't, then the matrix is not diagonalizable. So definition. A square matrix, or an n by n matrix, A is diagonalizable if there is an invertible matrix P so that P inverse times A times P is a diagonal matrix. That's the definition. Now, up to this point, I've been talking about eigenvalues, eigenvectors, eigenvalues, eigenvectors, whereas here I'm just, is there anything about eigenvalues and eigenvectors in this definition? No. So what's the connection? So theorem. If A is diagonalizable, then the columns of P are eigenvectors, and the diagonal entries of the diagonal matrix are the corresponding eigenvalues. So this tells us that if you're able to diagonalize a matrix, then the columns of P must be eigenvectors and the entries on the diagonal must be eigenvalues. So proof. I'll do it for the 3 by 3 case. If you understand the 3 by 3 case, you understand it in general. So assume A is 3 by 3 and P inverse AP is lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. So we've assumed that A is 3 by 3 and A is diagonalizable. Then A times P is equal to P times lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. I multiply it on the left by P. We write P in terms of its columns. So then A times P is A times the first column, A times the second column, A times the third column. That's just A times P. On the other hand, P times that diagonal matrix is the same thing as lambda 1 V1, lambda 2 v2, lambda 3, v3. If I know that this equals this, it's the exact same thing as knowing this equals this. The first column here must be the same thing as the first column here. The first column here must be the same thing as the first column here. The first column here must be the same thing as the first column there. Is v1 an eigenvector? If v1 is an eigenvector, then when you multiply a times v1, you're going to get some number times v1. That's the first condition. So certainly a times v1 is equal to lambda 1 times v1. What's the second condition for an eigenvector? Can v1 be the zero vector? No. Is there any risk that v1 is the zero vector? If v1 were the zero vector, would p be invertible? No. For sure, this is a non-zero vector, because if it were a zero vector, p would not be invertible, and p is invertible. So this is a non-zero vector, so that a times v1 is lambda 1 times v1. It's an eigenvector with eigenvalue lambda 1. v2 is non-zero because if it were a zero, p wouldn't be invertible. So this is a non-zero vector, so that a times v2 is lambda 2 v2. v3 is a non-zero vector because otherwise p would not be invertible. v3 is a non-zero vector, so that a times v3 equals lambda 3 times v3. It must be an eigenvector. So the diagonalizability is exactly the same thing as being able to find a linearly independent collection of eigenvectors. So let's do two examples. So A is the matrix minus 7, 2, minus 4, 8, minus 1, 4, 18, minus 6, 11. And the question is A diagonalizable? So the first step is to find the eigenvalues. So that means I need to compute the determinant of A minus lambda I. This is going to be what degree polynomial? Third degree polynomial. And after 5 minutes of calculation, involving numbers like 48 and 18 and 88 and 72 and 16 and 30, I get minus lambda cubed plus 3 lambda squared plus lambda minus 3 is 0. So that took me probably not 5 minutes, but certainly 3 minutes in my office. Now I seek roots. Does anyone have the cubic formula memorized? The quadratic formula? Yeah, good. You've got the quadratic formula memorized. There is a cubic formula which you could memorize. It takes about a page. If you have it memorized, you would just take the coefficients minus 1, 3, 1, minus 3. If you were Wolfram alpha, you would have the cubic formula as one of the subroutines, and you would just be able to give out the eigenvalues, the roots exactly. But this is out of a math book, and if I haven't made any mistakes, this is going to be something that we can find at least one root for. Because if we can find one root, we can factor out lambda minus that root, and then we'll be down to a quadratic polynomial, and you can use the quadratic formula. So can someone please give me one root? A number that's satisfied, that when you plug it in, you get 0. 1. Okay, for those of you who didn't know how other people got that, this coefficient is always going to be 1 because it comes from the leading term here. This is always going to be 1 or minus 1. So then you're just trying divisors of this. So if this were a 6, you would try 1, 2, 3, 6, minus 1, minus 2, minus 3, minus 6. And you always try the small numbers first. So this is a 3, so you try plus and minus 1, plus and minus 3. And if those don't work, then you panic. But in fact, 1 is a root. So lambda equals 1 is a root. This tells me that, that the determinant of a minus lambda I, which is the characteristic polynomial, which is minus lambda cubed plus 3 lambda squared plus lambda minus 3, can be written as lambda minus 1 times something quadratic. Now, at this point, you can either do long division or you can do synthetic division. Google it. I will do long division. So I'm trying to divide lambda minus 1 into minus lambda cubed plus 3 lambda squared plus lambda minus 3. To knock out the minus lambda cubed, I'm going to have to multiply that by minus lambda squared. This times minus lambda squared is minus lambda cubed. This times minus lambda squared is plus lambda squared. Now I subtract, this minus this is 0. That was the whole point. This minus this is 2 lambda squared plus lambda minus 3. Now I want this to match with that, so I do plus 2 lambda. So this times that is 2 lambda squared. This times that is minus 2 lambda. This minus this is 0. This minus this is 3 lambda. This minus this is minus 3. What do I put up here? 3. And am I happy? Yes, I'm very happy. So I got that my characteristic polynomial so the determinant of a minus lambda I is lambda minus 1 times minus lambda squared plus 2 lambda plus 3, which is minus lambda minus 1 times lambda squared minus 2 lambda minus 3, which is minus lambda minus 1. Can I factor that? Yes. Lambda minus 3, lambda plus 1. So my eigenvalues are 1, 3, and what? Negative 1. I now have to solve 3 different AX equal B problems to find corresponding eigenvectors. For this one, I get anything of the form t times minus 1/3, 2/3, 1. For this one, I get anything of the form t times minus 1/3, 1/3, 1. And for this one, I get anything of the form t times minus 1/2, 1/2, 1. If I wanted a pretty matrix, what would be a pretty choice of t? 3. Minus 1, 2, 3. Pretty choice of t? 3. Minus 1, 1, 3. Pretty choice of t? 2. Minus 1, 1, 2. And the diagonal matrix, what's the first entry going to be? What's the eigenvalue? 1, 3, negative 1, 0, 0, 0, 0, 0, 0. And you can check that P inverse times A times P is equal to this matrix. If I had shuffled the columns, I would shuffle the diagonal. If I multiplied the columns by non-zero numbers, I would get the same diagonal. And The big question is this puppy invertible? And we will start class tomorrow with yes.